In this third video on autonomous systems, we'll consider several population models. We take as the starting point the case of a single variable. The most basic model is that in which a single species, so a species x equals x of t, t of course is time, x is the single species, and it's growing or decreasing at a rate proportional to its current population, which is another way of saying that it solves the differential equation x prime equal ax, where a is a constant, and the population is growing or decreasing according as to whether a is positive or negative. So this is clearly a single first order ODE, autonomous, so it's autonomous because there's no t on the right hand side. And the population that x represents, as I said, is either increasing or decreasing according as a is positive or negative. So if we restrict our attention to non-negative x's, after all, negative population really has no meaning, then the phase line, so the phase line, which you encountered earlier in the course, for x looks like this. Here's 0, and then so there are basically two possibilities. Either the population stays steady at 0 or it increases to infinity. That corresponds to a positive, and the other way is like this, and that of course would correspond to a negative. Okay, in this video, in this exercise, we'll assume that a is positive, that we have a growing population. Now we see from the phase line that this simple model predicts unrealistically that the population grows without bound. So a more realistic model imposes a so-called logistic condition, in which case the differential equation becomes x prime is equal to ax minus bx squared, where again a and b are positive constants. Continuing with our logistic model, let's draw the phase line. This time there will be two critical points at 0 and at a over b, and in between, to the left the curves are increasing, and to the right the curves are decreasing. So 0 is unstable, and a over b will actually be an asymptotically stable critical point. Even more realistically, we can change the logistic model to a so-called logistic with threshold model. So logistic with threshold. And as usual, I've forgotten how to spell threshold. I'm not sure if it is in nature too. But in any event, the model is as follows. X prime is equal to minus ax plus bx squared minus cx cubed. And again, a, b, and c are positive constants. And then the phase line for this model will have 3 points, 0, let me call it for the moment alpha and beta, where alpha and beta are given as follows. A little bit of algebra, 1 over 2c times b plus or minus the square root of b squared minus 4ac. And we will assume here that AC, A, and C are small with respect to b, so that the square root is the integrand, the quantity inside the square root is a positive number. And so our phase now looks as follows. Down here the curves are going this way, and the other curves are all converging to beta. So 0 is asymptotically stable, so is beta. Alpha is unstable. And what it says is that for population models that start out with population less than alpha, they will die out to 0. But any place else bigger than alpha, the curves will converge to beta, except if you start at alpha or beta, in which case the curves are stable. They don't move. And so again, alpha, 0 and beta are asymptotically stable, and alpha is unstable. So we've given 3 distinct models for a single species, depending upon whether there's a logistic or threshold condition. And we will use those in a moment when we turn to systems, 2x2 systems of differential equations, autonomous, which model a population problem. The 2 primary examples of population models that give rise to 2x2 systems, which we study in this course, are competing species and predator-prey. So let's take them one at a time. First, competing species. So we have 2 species in the same environment and they're competing with each other. We assume that if left alone, each one of them satisfies a logistic growth equation, but then when they interact to their mutual detriment, and the resulting system becomes as presented here. So here is the logistic part for population X. Here's the logistic part for the population Y. And then here's the 2 interactive parts. When X and Y interact, it acts as a check on the growth of both of them. And I factored out the common factors here. X is common in the first, Y is common in the second. The coefficients are determined by the logistic and the growth parameters of each species. The A and D are the growth parameters, the B and the E are the logistic parameters, and the C and the F are the parameters determined by the interaction. Now, in the most interesting instances, the 2 lines represented by the zeros of the linear expression in the parentheses on the right. So this here, the set of points x, y, where a equals bx plus cy, is a line in the first quadrant with negative slope. Similarly with this one, and so the most interesting case is where those 2 lines intersect. At the point where they intersect, we get a critical point, the sole critical point, inside the first quadrant. There are 3 other critical points. One is at the origin, and the other 2 are at the logistic points on the axes for the 2 species. Now, depending on the relative size of the coefficients, as you've seen in the course, one has either the so-called doomsday model or the peaceful coexistence model. The doomsday model is where, with the exception of a separatrix, any start point inside the first quadrant leads to the death of one or the other of the species. The peaceful coexistence model is where any non-trivial start point inside the first quadrant leads to a certain fixed, stable critical point where positive populations exist for both species, and so that's why it's called peaceful coexistence. These models are considered at some length in the notes. Here I'm going to look at a somewhat different special situation in which the inherent logistic behaviors are identical. The logistic behaviors are identical. And as I say here, the interaction hurts or benefits one species in inverse proportion to how it helps or hurts the other. So let me take a representative example of a system like that. I've basically taken the growth constants and the logistic constants to be 1, and since logistic parameters for the two species are the same, these are all 1s. And then, of course, the interaction for each of them, it's really the interaction, which is the constant of interaction, which is inversely proportional. So I'm taking beta for this guy and 1 over beta for that one. And I'm really, of course, assuming that beta is not equal to 1. Of course, if beta were equal to 1, then these would be identical. The formulas on the right-hand side would be the same. And every point on the line x plus y equal 1 would be a critical point. So we would not be in the case where critical points constitute an isolated set. This would be an unusual situation. The phase portrait in that case will take an unusual form, and I'll draw it in a moment. But first, we observe that when beta is not equal to 1, then there is a point of intersection, and we'll compute it in a moment. The phase portrait is different from those for both the doomsday and the peaceful coexistence models, but it turns out it's actually reminiscent of one of them, as we shall see momentarily. So now let us turn to MATLAB to see what these phase portraits look like. Okay, so as usual, we will use MATLAB to do our analysis of these systems. Let's start off by clearing everything. And the next thing we do is compute the critical points of the system. Notice here, put in the system exactly as it was on the previous sheet, and I solve it. And here's the analysis, but first let's run it. And we bring up the MATLAB window. And there's our critical points. The origin, 1, 0, and 0, 1. Notice they don't depend upon beta. Get the same critical points regardless of the value of beta. Okay, so now we want to do a little almost linear analysis. I'm going to compute the Jacobian matrix of the partial derivatives of the system, find the eigenvalues at each critical point, and based on the results, we will classify the critical points. So let's run it first. Here they are. Run it. Bring up the MATLAB window. And here we go. The eigenvalues at 0, 0 are 1, 1. The eigenvalues at 0, 1 are, here they are, minus 1 and 1 minus beta. And here's the eigenvalues at 1, 0. So here we have two positive repeated real eigenvalues. Obviously, this is going to be an unstable node. And what happens here depends upon whether beta is bigger than 1 or not. And let's go back to the editor window to see the summary. If beta is bigger than 1, the origin is, as I said, an unstable node. 0, 1 is an asymptotically stable node, but 1, 0 is an unstable saddle point. Don't know how that got in there. Saddle point. If beta is less than 1, the natures of the eigenvalues at the 2 points on the axes are reversed. Okay, so after examining the eigenvalues, we see that when beta equals 1, then 0 becomes an eigenvalue. So let's quickly look back at the MATLAB window. Right? If beta is equal to 1, 0 becomes an eigenvalue. And so our usual almost linear analysis doesn't apply so well. So let's consider that case separately, and then we'll return to beta not equal to 1. So when beta equal 1, the critical points are all the points along the line x plus y equal 1. And then you have the additional single point, the origin 0, 0. So let's first draw the direction field, the vector field. There it is. And you can see here's the line x plus y equal 1. Blow this up a bit. Right? And I've got all these coming in along straight lines heading for the origin. They're going out straight lines heading for the origin. And every point along the line x plus y equal 1 is a critical point. So this is a picture you haven't seen before. All the solution curves are converging to the line x plus y equal 1. And which point they converge to depends upon which line emanating from the origin they are on. So to plot the phase portrait of the system, I'll use the approach from the Doom book. In this case, I'm going to use a grid of points along lines parallel to the 135 degree line x plus y equal 1 to generate different initial conditions. It makes for a better picture. Let's draw it. So there are and they see all the solution curves doing exactly what we saw before. And now finally, let's combine them. So here I'm combining, and I have to bring that graph back up. So there's the direction field and the phase portrait for this very unusual situation where the logistic model is exactly the same for both species. Nothing too typical. The odds of that happening are really rather small. And I even refer to it as a degenerate system. So now let's look at a non-degenerate system, that is where beta is not equal to 1. And so I'm going to choose as a representative value beta equal 1.5. So first let's draw the direction field, vector field. And what's happening here? So these curves are coming in and these are going out, and what's happening is if you're on the x-axis, then of course this point right here is an asymptotically stable point. That's the logistic point. But as soon as you get off the x-axis, as soon as there any y population, all the curves are converging here. So it's somewhat like the doomsday model. If there's no y population to begin with, x stabilizes, but if there's any y population, x dies out and y tends to its logistic point. Okay. Let's draw the phase portrait. I'm going to leave it to you to look at the code. And same kind of thing. You see all the curves are converging to the point 0, 1. And incidentally, there's a little bit of extra code here where I had drawn the curves for negative values of time, but it really didn't do anything for the picture, so I commented them out. Let's combine the two, the phase portrait and the vector field. And if we do that, there it is. Right? So this is again sort of a it's partly doomsday model. As soon as you have positive populations, x dies out and y converges to its logistic point. Okay, so now let's take a value of beta less than 1. You should be able to anticipate the result. Hopefully think about it a little bit before I draw it. What's going to happen? I'm going to take beta equal 2/3, and let's draw the vector field. And you can see what happens. In this case, the y populations die out and everybody's converging to x, the logistic point of x right here. Okay. Looks like there might be a separatrix. Huh? Right? If you, very close to here. I mean, the separatrix isn't really separating behaviors. Above it, the curves are coming down. Below it, the curves are going up, but they all converge to this point 1, 0. Okay, here's the phase portrait. Takes a little bit to compute, but not too much. And everybody's converging here, as we expect. And finally, let's put the two together. And our picture then looks as follows. Right, there's sort of, again, part of the doomsday model. As soon as there's any positive x population, y dies out and everybody converges to the logistic point of x. Now we'll turn to predator-prey, and we'll look at 3 examples. In every one, we'll assume that the predator takes the following form. If left alone, he has nothing to eat, and so satisfies a basic exponential decay equation. Then we'll put 3 different assumptions on the prey. When left alone, either it satisfies, in the first case, a simple exponential growth equation, or we will assume that it assumes a logistic growth equation. And finally, the third example is when it has a logistic growth with threshold constraint on it. And then we'll use MATLAB to examine the 3 different behaviors that emerge. I'm going to look at 3 representative examples, and here they are. In every instance, the predator equation, which is the second, it's just minus 2 plus x. That is just the typical exponential decay. And then for the prey, either it is a simple exponential growth, or a growth with a logistic term, or in this last case, a growth with a logistic and a threshold term. Now we'll sig MATLAB loose on these 3 examples, and we'll see what emerges. So as it says here, we'll run through this quickly. You're invited to examine the code in more detail at your leisure. Also, I will only draw the phase portraits and vector fields. You're also invited to work the relevant problems in problem set F in the MATLAB book in order to see how you can use MATLAB to compute the critical points, examine the nature and type of their stability, and to draw separatrices. So as usual, we clear everything. And now let's look at our first example. This is the case where the predator has exponential decay, the prey has exponential growth, they interact. to the benefit of the predator and the detriment of the prey, but there's no logistic or threshold. And let's just look at the code briefly. This is the vector field, and then what follows is the phase portrait. It's done all together, so let's evaluate this. And there it is. This is the stability point right here, 2, 3, and in fact these are closed curves. So this is a situation where you have a center, and the solutions are oscillating around that center. So the populations are going up and down, both the predator and the prey. Okay, second example. Same as before, except now there's a logistic term. That's the term right here. So that puts a constraint on the growth of the prey if there were no predators. The code is the same, just the change of the formulas here and here. Let's run it. And this time we get a asymptotically stable critical point right here at 2, 1. And so all the populations are honing into that point right there. Make it a little bigger perhaps. And you can see the asymptotically stable spiral point right there. And finally, let's add in the threshold. So there it is. There's the threshold term. And let's compute now the vector field and the phase portrait. And we get this picture here, which is somewhat reminiscent of the cover of the MATLAB book. This is a nice asymptotically stable. It's hard to tell from the picture whether it's a spiral or a center, but in fact it's a spiral. And curves here are coming in and going around. But up here, they come and crash. And so there's actually a nice separatrix here, which is considered in some of the other problems. And in fact, in one of the other videos, above it, the populations die out. And below it, they circle around into this, spiral around into the center, and you have a nice peaceful coexistence. So those are the three possibilities that can arise. So the hope is that you take away from this video some understanding of these population models, the competing species and the predator-prey, the kinds of phase portraits that can arise, and the nature of the populations in the long term. That's it.